Hello students, welcome to today's lecture. Today we're going to see how to use the equations of motion. Okay, the equation of motion was derived in the last class, so you can go through the derivation if you haven't yet. Okay, in momentum shell balance we'll solve three problems, right? The falling film problem, then flow through a circular pipe, then again we have flow through annulus, right? So we'll go through the all three problems, but this time we are not going to solve using momentum shell balance. We're going to solve using the equation of motion. Okay, so how to proceed? Okay. So first one, this is the falling film problem. Okay, so first you have to read the problem carefully, then make assumptions. Okay, so in the falling film problem, what were the assumptions? Were assumptions of, what are the assumptions? First assumptions, write down the assumptions first. First, it is incompressible flow. Incompressible flow. What do you mean by incompressible flow? Incompressible flow means density of the fluid is constant. Okay. Then we have steady flow. I mean steady state. Steady state flow means there is no dependence upon time. So anything there by time will be strike off. Okay, the flow is not dependent on time. So anything which is changing with time will be strike to zero. Okay. Then thirdly, fully developed flow. What do you mean fully developed flow? Fully developed flow means if the fluid is flowing in this direction, the velocity, let's say I have, let's first set the axis. Let's say this is y, just for example, okay, this is x. So fluid is flowing in this direction, so the vy. So vy will not be function of this direction of flow. That is vy will not be function of y. This means the flow is already developed. Okay, it is not a function of any distance more. Generally, with time, how the flow will develop. This is the entrance, so it will start developing, right? This, like this, and ultimately it will gain this. It takes some time for the fluid to achieve this complete profile. Okay. So we are ignoring this part. Okay. So we are assuming that it is only fully developed. So the profile is same everywhere. This makes that the flow is not a function of the distance in the direction of flow. In this case, Vy is not a function of y. This is the fully developed flow. And lastly, you have to assume that the viscosity is constant. Okay. So viscosity is constant. It's not a function of x, y, g or time. Okay. Again, you can also assume that it is Newtonian fluid. It is Newtonian fluid. Okay. If you are assuming Newtonian fluid, then you can use this relation directly. So that was minus mu dvx. See, the vx is the first index, is the direction in this flow, and momentum is getting transferred in y direction. Okay, you can directly use this relation for all coordinate systems if it is a Newtonian fluid. If it is non-Newtonian fluid, then we'll have some power here. So it is really difficult. Okay, so in this course we are not going to study non-Newtonian fluid. Okay, so assume that it is Newtonian fluid. Okay, also apart from these assumptions, you can assume it is based on the problem actually. So I think this part is clear, so I will erase it. So these are the main assumptions. And from the problem, you can write down other, other assumptions as well, like not assumptions, but from the problem actually. So let's say we are doing falling free problem, right? So here, so set the coordinates. So definitely you can set the coordinates like this, but this is inclined, right? So it will be easy if you choose this coordinate system. So here in this problem we choose z direction. This was x. We would have chosen x only, but because the fluid is from this exerting pressure on this direction, so assume x in this direction. So using right hand thumb rule, then what will be the y direction? The y direction will be x cross y. So y direction will be in this direction. Okay, so let me check it. Okay, y direction will be in this direction. Okay. Now, the obviously if you choose this coordinate system, then fluid is flowing in this direction. So Vz. Okay. Now, definitely Vz is not a function of z direction in this direction because it is fully developed flow. Okay, you already assume that, and there is no flow in x direction. Okay, so Vx is 0, Vi is 0 because there is no flow in this y direction or x direction. Okay, now pressure will be a function of x direction because we have a fluid exerting pressure on the bottom fluid. So pressure will be in this direction. Okay, this is falling free problem. Okay, and what else? Nothing else. Okay, so definitely this is the gravity. So you have to take the component of gravity in this direction, right? So it will be g cos beta in this direction, the component of gravity. Here also it will be g sine beta. Anyway, you can use this, but it will automatically get 0. Okay, so you can ignore this part. So okay, so your problem formulation is ready. Also, you can write down the boundary conditions, but for now you don't need boundary condition. Once we integrate the equations, then you can apply the boundary conditions, or you can write along with the assumptions also. No problem. Okay, so once this is set, now we'll directly go to the equation of motion. Okay. So you can directly solve for velocity profile, or you can use the shear stress formula. Okay. So what I'm saying is, yes, this one. So you can directly use this one. See, in this formula we have shear stress. Okay, or you can directly use the velocity equation to get the velocity profile. But suppose in the problem it is asked to find the shear stress profile. So it will be better to integrate this equation, okay, in terms of shear stress. Or if you prefer to directly use this equation first, then use this, solve for Vx first or Vy, whatever. Then you can, using Newton's law of viscosity, you can again, find the tau Ix. So you can go to the Newton's law. Yeah, from here you can find the velocity, shear stress again. Okay, so you can have two approaches. You can directly use the equation of motion in terms of velocity. Okay, find the velocity profile. Then you can calculate the shear stress. So find the velocity profile first. Then you can find the shear stress. Okay, or you use shear stress, find the shear stress profile, then put the Newton's law of viscosity, then find the velocity profile. Okay, you can do by both approaches. So I will use this one. Okay, First, I will find the shear stress, because in the problem it is asked to find the shear stress. I will follow this one. First, I will find the shear stress profile. Then I will put the Newton's law of viscosity formula. Then I will find the velocity profile. Okay. Okay. So always, now everything is ready. So first you have to solve the continuity equation. Okay. So if you solve the continuity equation, okay. So this is the continuity equation. Always solve continuity equation first. Okay. So we have cylindrical system, right? Right, X, Y, Z, and you have chosen the coordinate system in this for the falling film problem, right? So follow that only. Just you have to plug in the direction values here. Now solve the continuity equation. We are using Cartesian coordinates. So for falling film problem, we have assumed incompressible flow. Rho is constant, and it is steady state, right? So if it is steady state, then this terms goes 0. So density is not a function of time, X, Y, Z. Okay. Similarly, the rho can be taken out, right? Because it is constant. And then Vx is 0, right? So this term is 0. Vy is also 0. So this term is 0. Vz, however, Vz is not 0, but it is a function of X, not Z. So this is also 0. So from continuity equation, we did not get any equation, okay? Because the flow is incompressible, okay? Sometimes in cylindrical coordinates, you might get some relation, but generally you will not get for incompressible, okay? So this whole term is 0, okay? Now, once you solve the continuity equation, go for equation of motion, okay? I told you I will first calculate shear stress, then I will calculate the velocity, or you can do the vice versa. So in this problem, I will follow this Cartesian coordinates and in terms of shear stress. Okay. So first I will solve the equation of motion in the x direction. So Vx is 0, right? I mean, you can set this equal to 0 because it's steady state, or Vx is 0. Okay, rho is constant, it is taken out. Okay, so Vx, now Vx is again 0. So this term will be 0. Vy is 0, so this whole term will be 0. Vz is not 0, but Vx is 0, so this term will be 0, right? However, the pressure is a function of x, right? So this term will be there. What about tau xx? So tau xx, you have to calculate from tau xx is nothing but minus 2 mu d Vx by dx. Again, it will be 0, right? Because Vx is 0. What about tau ix? So it will have the term minus mu, this term minus mu dou Vx by dou y. Again, Vx is 0. Again, this will be 0 because Vx is 0, right? And you can calculate the gx, right? What was the gx in the direction? So the g, what was the component of gravity in that problem? So component of gravity in the x direction was g sine beta. You can put it here. So it is g sine beta. Okay. Again, Vy is 0, this is 0. Vi, because Vx is 0 and Vy is also 0. Vy is 0. Vy is 0, so everything goes down. There is no pressure gradient in y direction, so 0. Again, these all components will have Vy, so all will be 0, and there is no component in y direction, right? So 0. So this equation will not give anything. So 0 equal to 0. Now solve the third equation. So for third equation, you have this steady state, so no change with time, 0. Vx is 0, Vy is 0, Vz is non-zero, but it is fully developed. Vz is not a function of z. Okay, so this term will be 0. And there is no pressure gradient in z direction, 0. However, So xz, so vz is, this term will be there because vz is a function of x, so it will be there. What about this? The vz is not a function of y, so this term will be 0, right? And tau zz will be there because this will be vz, right? Vz is not a function of z, so this term will be 0. And there is component rho g cos beta, right? So you have got three equations. So just write down. So if you write it down, you'll have minus dou p by dou x, dou p by dou x, and you have plus rho g x, right? X was sine beta. This was one equation, and the second equation was minus and plus, right? So minus dou tau xz dou x plus rho g z, that is rho g cos beta. Okay, now integrate this two equation. So it will get, if you integrate this equation, you will get p equal to rho g sine beta x plus c. Okay, so if you solve this equation, second equation, then you'll get, if you get here, so tau xz is equal to rho g cos beta x, right? So x plus c. Right? So you have found this the shear stress equation. Now you have to integrate, or you have to apply boundary condition to remove this constant of integration, right? So in the falling film problem, where is the shear stress 0? Shear stress is 0 where, if this is the falling film problem, so this is your plate wall, so this shear stress is 0 at the air and liquid interface, right? This is the boundary condition here. So this was your starting of the coordinate system, so it was 0. So tau xz is 0 at x equal to 0. So if you put this boundary, then you will get c equal to 0. That means tau xz is equal to rho g cos beta. Okay, so you have got this shear, this one x, so shear stress profile. Okay, then for pressure, you can use the boundary condition. So at x equal to 0, at the surface, what is the atmospheric pressure, right? P is equal to P naught. Okay, so if you write it down, so if you put this boundary condition, so this will become 0, and C is nothing but P naught. So you'll get P minus P naught equal to rho g sine beta x, right? So this is nothing but pressure difference if you come down in the direction of x. You can also get this pressure profile. However, this was not calculated in the momentum shell balance example of the falling film. Okay, but this is the how the pressure is changing in the x direction. Okay, now if you have got this shear stress profile, right? You can cross check with the earlier, so you have got the same, right? So this right. Okay, now we'll solve for velocity profile. So to solve for velocity profile, you have to use the Newton's law of viscosity here. So what is Newton's law of viscosity for this shear stress xz? So it is nothing but minus mu again I will the final see. So you can use the complete equation as I told you earlier. So if you go up here, so now use this formula. So we have to use this which one? This one, right? Okay, zx. I want to find xz. So this is minus mu d dou vx by dou g plus dou vz by dou x, right? Now this term will be 0 because vx is 0. Okay, so we are left only with minus mu dou vz by dou x. So you can write it here. So it is nothing but dou vz by dou x. Just simply put it here, this formula here, and integrate. So if you write, it is nothing but minus mu dvz by dx. See, I can write now d because vz is not a function of other variables, only a single variable x. So you can easily write this one. It is no more a partial derivative. Okay, it is a single derivative because only one variable is involved, x. So it is equal to rho g cos beta x, right? So just take it here, the right side. So you'll get vz equal to minus rho g cos beta by mu and x, right? Just integrate this, then you'll get the vz equal to, you have to integrate from 0 to vz and definitely from 0 to x. You'll get vz rho g minus cos beta by mu x square by 2, right? So x square plus constant of integration. Now you have to use the boundary condition for velocity. So where is the velocity 0? So vz is 0 at the wall, right? So at the liquid and solid boundary interface. So at x is equal to delta. If you remember, we have coordinate system at this point, starting of the film, and at the wall it is this. So if the thickness is delta, then definitely x is equal to delta. We have velocity 0 here. So if you put it here, so you will get c is equal to delta square. Just replace the x delta square. So if you rearrange, so you will finally get the minus rho g cos beta 2 mu x square minus delta square, right? So if you can rearrange it and you'll get the final equation. So you can, if you see the previous formula, so it has done the same thing. You have constant integration. So it has used the same boundary condition. So you can rearrange, right? So you'll get this. Okay. So you have got the velocity profile using equation of motion. So and other things are same. Maximum velocity you have to calculate like this. Average velocity you have to calculate like this. Then you have mass flow rate like this, right? Film thickness, force. Other things remain same. Only to calculate shear stress profile and the velocity profile, you can use the equation of motion. Okay, so this was the falling film problem. Now we can move to the next problem.